Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the second tutorial, which is tutorial to math for AI. In the last tutorial we discussed about certain basic math operations. Now in this particular tutorial for mathematics for AI, let's go over calculus, let's go over the derivatives and integration, or something that we saw last time. However, let's take a look at these particular operations with the perspective of multivariable calculus. Since we are operating with since we are operating with multi-layer perceptrons, we do have multiple variables which are learnable, right? So multiple variables in the function. And hence let's look at their interpretation. Let's also look at what happens when we plot the error and what does it mean when we look at it from a 2D view, when we look at its contour. Okay, so let's start with using the derivatives to finding the extremum values of a function. Let's define f of x as x cube minus 12x, which is essentially we are using SYMS to define all the other variables. In this case it is xf and gh because we will be using that later. F of x is given as x cube minus 12x. Now essentially what we can do is use this particular code and use fplot to plot the curve. Again, we are not very will not take a deep dive into the syntax of it. We will maybe focus more on their interpretation of the math functions. So we essentially can plot f of x against x, which looks like this particular function, which is a cubic function. Essentially the x axis highlights the x values and f of x highlights the values of the function at the corresponding values of x, right? And if we observe the curve, we can see that there are points which actually which could actually mean local minima or global minima, right? Now let's take g of x, which is the first order derivative of f of x, and let's use the command diff to get the differentiation of the function. Gx is equals to diff f of x. Now once we have g of x, we'd like to plot g of x as well. Now g of x is essentially a parabola which is observed here. So we have on the x axis we have x and g of x is the corresponding values, and we see that this is a parabola itself, which is the first derivative of f of x. Let's also take one more derivative, which is h of x, which is the second derivative of f of x. It can be obtained again using the diff function. So let's try to diff h of h, let's define h as diff of f dot 2, which is the double derivative, right? If we do that, we observe that the plot of the second derivative of f of x is given as a linear line, right? Now for a function f of x to have a local minima at x minimum, the following constraints should be satisfied. G x of minimum is equals to 0 and h x minimum is a positive number. Hence we try to get x minimum using the MATLAB syntax, which is double, which will specify the floating values. Solve g is equals to 0, which is essentially given as 3x square minus 12, and h should be positive again, so it should be 6s greater than 0. Solve these both equations for the variable x itself. Similarly, we could also focus on local maxima at x max, and we should try to satisfy the following conditions. G of x max is 0, h of x max is less than 0, and we can do the same, we can use the same solve operation to get x max as well. So g of x max is 0, h of x max is 0. Use it in the solve, using the solve operation in MATLAB. We can solve both of these equations simultaneously. Okay. Now also let's take a look at the first principle of differentiation. The derivative of any function, let's say f of x, can be defined as f dash x is limit delta x tending to 0, f of x plus delta x minus f of x divided by delta x. Let's assume we define the step size h to be very small and around an arbitrary point x0. Then we can actually write f of x as f x0 plus delta x given as f x0 plus delta x times f dash x0. Now if we start from a non-local maxima or non-local minima x0, essentially if we start from a randomly initialized x0 and take steps along the direction of the tangent, which is delta x times f dash x0, essentially looking at this particular part of the equation. At these points we reach the local maxima or minima. Now this actually is a very important part for our gradient descent learning algorithm. Whenever we move across a step size in the direction of the tangent, which is given as f dash x0, we are actually moving towards either a local minima or local maxima. So the ascending and descending along the slope of a tangent can be a way to optimize any function to find a particular minima or maxima. Now let's try to plot this function using the let's try to plot the function and observe the ascent or descent towards the local minima or maxima. If we look at the curve on the right, we observe that if we start from a point, say randomly initialized point of -4 comma -16, and we try to follow the same ascend or descend algorithm, we would see that the direction actually gives us a reference and we move towards the global maxima. And similarly, if we keep following the same trajectory, we would essentially reach the direction of local minima. Right. Now although this does seem to be trivial, this particular point is very important for us for our learning algorithm, which is we define a point x0 and take steps along the direction of the tangent, which is given as delta x cross f dash x0, and hence this would help us to reach a minima or maxima point, local minima maxima point. Okay. Now we have been looking at univariate functions, which is essentially focusing on only one variable, but let's look at a more realistic application of more than one dimensional. So essentially let's see what would happen if we are working with multivariable functions. Okay. So let's assume we define z as f of x comma y and we want to compute the partial derivatives with respect to x and y, and in MATLAB we use the function diff. X dot, which is the differentiation of x, is given as dou f of xy by dou x. Essentially we are trying to differentiate the function f of x with respect to the variable x itself. Y dot is dou f of xy divided by dou y, which is essentially taking the derivative with respect to y, right. Now the vector, which is x dot y dot, is called the gradient of the function and it represents the direction of the tangent of the surface at the point xy. Again, to reiterate, this is an important point that we will use while we are using the gradient descent algorithm, that the direction of the tangent is important and which is the reference point for our learning algorithm. Now let us try to evaluate the gradient. SYMS xy is essentially trying to define the symbolic variables xy. Z is given as x square plus y square, which is z is a function of x and y. X dot is the differentiation of z with respect to x. Y dot is the differentiation of z with respect to y. When we get the gradient, which is a gradient z, it is essentially defined as x dot and y dot, right. Now let's try to plot the surface along the two variables. Okay. plotting the surface plot with using two variables. So let's assume that we have defined a function f(xy) which is given as x square plus y square. Let's again try to generate a plot the same way we did in the earlier tutorials as well, right. Now in MATLAB we use the command surf. So first of all let's define the grid, which is define the step size for x and y. So x and y is the mesh grid which starts from -5 reaches 5 with a step size of 0.1, and similarly even for the y, right. Once we do that, we can observe on the right the plot. So we have x and y axis, and we have the function xy which is z, which is x square plus y square. We can observe that this is a curve, right, and one interesting point is this is a 3D curve. However, if I only want to look at the xy projection of this curve, I can look at it in this manner, and we'll maybe look at a better example that would highlight some more features of this curve. Similarly, if I only wanted to look at say z versus an x plot, it would be in this manner. So I am looking at, so my in this case I have the z axis which is 0, 20, 40, 60, and the other axis is the y axis, right. And this is a way to visualize, but we will see that it does have some meaning and some interpretations that could be used. Okay. Now let's plot tangents on this particular 3D surface to understand what does it mean, right. Now to show the direction of the tangent, we use arrows using quiver function. Okay. Now essentially the important point is, if we reverse the direction of the tangents and plot them, we can see that they will direct us to the local minima. So we essentially want the opposite direction of the tangents on the curve, and in short we descend to the minima using the gradient information. Now we saw that gradient direction or gradient information is important to move towards the local minima or maxima, and if I take the reverse of the direction of the tangents, I would essentially direct towards the local minima. So let's observe that. So in the same function, if we just plot the arrows using the quiver function and identify only the negative of the direction, we can observe that the arrows are actually pointing outwards, and on a closer look it would actually highlight that the arrows point towards the minima part of the curve, essentially giving us the direction. Okay. Now let's essentially take a much cleaner look. So let's assume in one particular patch and look at its magnitude. If we do that, this patch actually makes it clear. We can observe that this is a yellow curve as we saw earlier, and we can observe the direction of the red arrow which is opposite to the direction of the tangent, right, and we can see that near this point it is actually becoming a little bit more flat. Now essentially if I start from any random point, I do get the direction of the local minima in this curve, right, and hence it does give me reference while I am designing my learning algorithm, right. Now let's so one last topic is, let's at the end also try to understand the tangent directions on the contour plot. Contour plot is something we saw in the first tutorial. So let's define z as x square plus y square and keep c as a constant, right. If we do that, x square plus y square, and essentially if it's constant, then the value of z would be highlighted by these contours. So along different values of x, y, we would have constant value of z. One way to again have a better interpretation of this is, if we look at this particular curve, I can see that along my z axis along my z axis, which is z is equals to c, I can see that these are constant values, right? And if I look at it in this manner, I can observe that this is a contour. It is kind of concentric circles, right? However, if I just look at this curve, it doesn't give me a lot of information. Okay, now let's just take a plain look on the xy axis on the contour plot. So essentially we have a 2D plane and we are projecting all the contours. This graph is essentially how it would look. So we have certain circles, certain parts of the curve where the value is 5. As we keep moving outwards, we can see that the value keeps increasing. Now one way to understand is, if I have z, which is x square plus y square, and I want to find the minimum point of the curve z, then I can observe from the contour plot, the 2D contour plot here, that I should move towards the origin point, right? I should, even if I start from let's say 35, I should navigate towards a point which enters into the circle of 5, right? And this is when the value of z would be minimum, right? Now we saw this in the 3D plot from z, but just looking at xy, I can still say that I know the direction where xy should go to minimize z, right? And this gives more clarity towards how the algorithm should be defined. One more thing is, this essentially is a very clean and a beautiful curve because it's very symmetric. Now let's take a different example. Let's look at a different curve, which is z is equals to x square minus y square, which is essentially identified by this curve, right? And let's try to look at its contour plot. The contour plot looks like this, right? So it's not a very clean concentric circle kind of a graph. It's a very what do you say? It's like a very it's a different curve. It's a harder curve because I can see the values are 5 here and very close to it is minus 5, and I have 0 here, right? So navigating through this kind of a space could be harder, right? And we will see the influence of normalization techniques and other heuristics which can be used to avoid this particular kind of a graph. So again, we observe it is difficult for an algorithm to converge in this case, as there would be steep fall on either side of the saddle point, right? So if I have a saddle point in the middle, I know that there are certain parts which are very high in value, which is 10, 15, 20, and just very next to it I have values of minus 10, minus 15, minus 20. Hence it does become harder, right? Because you can fall into either of these parts. And hence the ability to visualize the shape of the functions is therefore essential for us to design appropriate solutions, and also for us to understand why the particular algorithm is failing, right? Because if I just look at the 3D plot, I can see that okay, the algorithm should have converged, but it's not converging. I can actually look at the contour and see what is actually going on, right? Which variable is having more influence and which is causing it not to converge yet but to diverge. Okay, so this particular lecture or tutorial focused more on calculus, more on the derivatives and on multivariable calculus. Essentially we tried to see the plot on the 3D space, and we also try to understand what does it mean when we are navigating through the direction of the tangent, and what would it mean when we are looking only on the 2D space, which would only essentially have x, y. Thank you.